Hi, Mr. Pepperell here, and today I am revising P2 Topic 5, which is Mains Electricity. So the first part of work we covered in this topic was alternating current, and that included being able to interpret these things which is called oscilloscope traces. So the first part of my question says, what is the peak voltage of the power supply if the Y gain is set to 0.5 volts per centimetre? Now the Y gain is basically setting the scale of this Y axis on the plot here, and what they're saying is that for every 1 centimetre square, these are centimetre squares on the plot here, every centimetre square is worth 0.5 volts, so 0.5 volts per centimetre. So to work out my peak voltage, which is the top of my wave there, all I need to do is look at how many squares up my wave goes and then look at how much each square is worth. So basically all I'm going to do is, I know each square is worth 0.5 volts per centimetre. Okay, my wave goes up, 1, 2, pretty much 3 squares there, so all I do is 0.5 volts per centimetre multiplied by 3 centimetres tell me I've got a peak voltage of 1.5 volts. Okay, so that is the first part of the question done. I can work out the peak voltage. The second part of my question though asks me, what is the frequency of the power supply if the time-based control is set to 10 milliseconds per centimetre? Now the time-based control is basically the x-axis on our plot, so what they're saying here is that each centimetre square along the bottom is worth 10 milliseconds. So there's two parts to this. Firstly, I need to take out the time taken for one cycle of my wave. So one cycle is from the top of one wave to the top of another wave, or the bottom of one wave to the bottom of another wave, or the middle of the wave to the middle of the next wave. Any two similar points on the wave. Okay, so first I need to work out my time cycle. So what I'm going to do is I can see that each square is worth 10 milliseconds per centimetre. So 10 milliseconds per centimetre, it takes a total of 1, 2, 3, 4 squares for my wave to get back to a similar point. So I'm going to do 10 milliseconds per centimetre multiplied by 4 centimetres tells me I've got a cycle of 40 milliseconds. That's how long it takes for one wave to go. Okay, but what I want to know is the frequency, and that is how many waves are there, or how many cycles are there per second. If every 1 second, how many cycles of that alternating current are there? So basically what I need to do is take my 1 second, divide it by 40, because that's how long it takes for one cycle to take place. So I'm looking at how many cycles of 40 milliseconds are there in 1 second. So it's just 1 divided by 40 gives me 0.025, and it's frequency, so I measure it in hertz. That's how I'd answer that question. So the next bit of work we looked at was cables and plugs. Here's a picture of a 3-pin plug from the UK, and the question is asking me to match the parts of the 3-pin plug with the different materials that these parts can be made out of. So pause this, have a little think about it, then start again and see if you've got the answers right. So hopefully what you should have had here was, okay, firstly, what's made out of brass? Well, made out of brass is the pins of the plug. Why are they made out of brass? They're made out of brass because firstly it's a good electrical conductor, secondly it's hard, and thirdly it's not going to oxidize or corrode in the air over time, so it makes it ideal. Secondly, what's made out of copper? Well, the copper is the actual wires inside that plastic coating that we've got there. Okay, so why are the wires made out of copper? It's a brilliant electrical conductor, relatively low resistance, and it can be bent into whatever shape you need it. Okay, next one is rubber. Well, what's made out of rubber? It is the cable insulation. Why is it made out of rubber? Again, it can be bent to the shape you need, and also it's an insulator. It's not going to let the electricity pass through it and hurt the user of the plug. And last of all, what's made out of stiff plastic? Well, that is the outer casing of the plug there. Okay, again, it's an insulator, so it's not going to let electricity flow through it, and it's hard, so it's not going to get damaged during use. Okay, so just make sure you know what each part of a plug does and why it's made out of the material it is made out of. So then we moved on to electrical power and potential difference, which is where we first came across this equation. What this equation tells us is electrical power measured in watts is equal to potential difference measured in volts multiplied by current measured in amps. And using this equation, we could answer this question. What type of fuse would you use for a 24 watt 12 volt heater. Okay, now you might remember that fuses come with different ratings. This is a 5 amp fuse, this is a 3 amp fuse, so they've got different ratings there. We need to know which one we're going to put in this heater. Okay, so first thing I'm going to do is to rearrange my equation, because I need to know the fuse rating, or in fact the current through the appliance, to know what fuse it's going to use. So here we go, this is what I rearranged my equation for. You can see it's the same equation, this time it's rearranged for I, which is current measured in amps, and that's equal to power measured in watts divided by voltage or potential difference measured in volts there. Okay, so now all I need to do is substitute my figures in. I've got 24 watts, 12 volts. I'm going to substitute those into my equation. Okay, and what that then gives me is my current is equal to 24 watts divided by 12 volts, which is equal to 2 amps. But hang on, I haven't got a 2 amp fuse, I've got a 5 amp or 3 amp there. All you do is you choose the next fuse rating up. So if I've got a current of 2 amps through my appliance, I'm going to put a 3 amp fuse into that plug. So in our final piece of work in this topic, we looked at electrical energy and charge, okay, and this is where we first met this equation here, which says charge is equal to current multiplied by time. And you will remember, of course, that charge is measured in something called coulombs, current is measured in amps, and your time is always measured in seconds. And of course, we can also write that equation shorthand there as Q for charge equals I for current multiplied by T for time. And using this equation, we can answer questions like this. Calculate the charge flowing in 50 seconds when the current is 3 amps. So all I'm going to do is substitute in my two values that I've got here into the equation where they need to go. Okay, so first job is always substitute the values in. So I've got a current of 3 amps, I've got a time of 50 seconds, so it's just 3 times 50 tells me that my charge is 150 coulombs. So the final thing we did in our little bit of work on electrical energy and charge was met this equation here, which says energy transferred equals potential difference multiplied by charge. And of course we always measure any sort of energy in joules, potential difference again measured in volts, and charge always measured in coulombs. And as before, we can write this in shorthand, which just says E equals V multiplied by Q, Q for charge, of course. Okay, and this equation helps us to answer questions like this. Calculate the energy transferred when the charge flow is 30 coulombs and there's a potential difference of 4 volts. So have a go at that one there, pause this, and then start again when you think you're ready to check your answer. Okay, hopefully you've paused it and you've started again, and this is what you've done in your working out the problem. Okay, first thing to do is substitute in your values. So we had a potential difference of 4 volts that I've put in, a charge flow of 30 coulombs that I've put in. So all we've got left to do now is to solve that, and 4 times 30 you should be able to work out is 120 joules. So the energy transferred was 120 joules when the charge flow was 30 coulombs and the potential difference was 4 volts. So that is everything we need to know about mains electricity. Any problems with that, don't hesitate to tweet me at Mr_Pepperell or email me and I'll get back to you ASAP. Thanks for stopping by.